All right, should I start?
Yeah, so hi, morning everyone. I'm very happy that we managed to get Adam Kalai over here. Adam used to be a famous machine learning theorist, and he's, I think, the first person I know that decided that theory is less interesting in machine learning than practice. I think this was like 15 years ago or so.
But now I'm back.
But now he's back. Now he's back. So let's hear it.
There's theorems in
Let's
this paper.
theory.
This paper has only theory. So the audience, it's for you. But thank you so much for inviting me. I'm honored to be here. And I'm going to talk about why language models hallucinate. To get a sense of the audience, how many people here have experienced language models hallucinating on them? All right, great. This is joint work with some colleagues at OpenAI, Ophir Nahum, Eddie Zhang, and my collaborator Santosh Venkala at Georgia Tech. And if you look at the instructions that we publish, the guidelines we have for language models, they say things like the language model should express uncertainty or qualify its answers when it lacks knowledge. When it doesn't know something, it should say, I don't know, or it should express its uncertainty in some appropriate way. Okay, so that's one of our stated goals, and yet the language models, instead of saying, I don't know, they hallucinate. So let me give you an example. So the question I asked the language model was, what does PGGB stand for? Does anyone in the room know what PGGB stands for?
Well, probably more than one thing, right? In general.
Yeah, that's a guess, but does anyone have one specific thing? All right, well, I just proved to you that humans don't hallucinate like language models. Some people say, oh, humans hallucinate just like language models. The language model learned it from us. We don't. You'll see, nobody in the room started shouting things out. But if you ask ChatGPT, depending on which model and everything, but it came up with pooled growth and green bond. Okay, PGGB, that's... Okay, I searched on the internet, no results. It doesn't exist, that string. Public Gaming Group of Belgium. People in Belgium like to play games. Surely there's a public group of gaming group. No. Personal growth and Golding, that sounds like such a common term, but no, it didn't exist. So, it made up a bunch of things which don't exist. It's not specific to ChatGPT. You ask DeepSeek, you get the permutation of Go given barriers, strategy in Go. You ask Claude, this is my favorite, the Pacific Gas and Electric Company, which doesn't even have a B. Sometimes abbreviated as PGGB in certain contexts, though PG and E is more standard. So the language models, it's funny, but it's also very serious. They're hallucinating. And so what does it mean? It's not a good thing when an error, not a good thing for AI when the error becomes the word of the year. Hallucination was the word of the year in the dictionary. And basically, it just means it produces false information. So it's something not true. And we could argue all day about what true and false mean. For this talk, we'll just consider a set. So it's going to be easy to think about it. We're not going to get into the definition of what is true and false. We'll assume there's a set of true and false. And the person in this dictionary asked the question, actually, one of their things was actually the research question of this talk was why do generative AI tools hallucinate? So maybe you can find other interesting research questions in the dictionary. But one of the key factors behind hallucinations is it's often much worse than just saying, I don't know, or somehow acknowledging the uncertainty. So why do the language models say stuff when in a normal situation, any person in this room, we were all quiet when I asked that. There's some misconceptions that I see that it's going to be easy for people in this room to understand, but it still sticks around. So people think often they look at hallucinations, they look at accuracy, and they say, our accuracy, let's check our accuracy. But it's not about accuracy, because you have accuracy and you have errors, but then you also have the possibility of indicating uncertainty. You can say, I don't know. Or I say I don't know here, that represents some way of politely indicating that you don't know the answer. So it's really the error rate that measures hallucination, not the accuracy. So you got to have 80% accuracy, that's pretty good. The question is, are you wrong 20% of the time, or are you saying I don't know 20% of the time? Another thing is that people think that making a language model that doesn't hallucinate would require many parameters. Actually, some of the dumbest people I know are quite humble. They don't. It's quite easy for me. You ask me a question in Russian, I'll tell you I don't know the answer. It's easy. I know, I don't know. If you know some Russian, do you know some Russian, Avi? I don't know. Okay, let's see, ask somebody who knows some Russian. I'm sure someone in this knows. Yeah. They have to think, do I understand the question? So it's actually easier. So I think that's a great challenge for academia. May not have the same resources, but prove the concept. Make a small language model which doesn't hallucinate and show everyone how useful it is. I think it'd be a great demonstration, and then people can port it over to the bigger ones. Another misconception is people think, well, eventually we'll get to 100% accuracy. Let's just keep improving our accuracy until we get to 100%. Of course, the problem is that there's always going to be questions that you can't find the answer to. Personal questions, things where the information isn't aligned. It's too hard, a math problem that's too hard for the language model. And then you need it to say, I don't know. And there's a lot of questions like that people ask where there's no answer available. So you might think the flip side, hallucinations are inevitable, because there's questions that we'll never be able to answer. No, obviously the language model should just say, I don't know, or somehow express. Okay. All right. So some people think misconceptions, some people think hallucinations have been solved somehow, and other people think language models will always hallucinate. I say neither of those are true. We're making progress. The language models are hallucinating less, but we're not there yet. But eventually, I do hope they'll hallucinate at a very low rate, similar to humans.
Can I ask, is
Sure.
it actually obvious that you could say, I don't know, on, like, there isn't some Gödel incompleteness or something?
I don't mean like 100% of the time, but people in this room at a very low rate, don't hallucinate, and I think that it should reach that very low rate. But yeah, to get 100% or 0% hallucination might be tricky depending how you define it. I mean, you could start with a chatbot that only answers calculator questions and no other questions, and then it doesn't hallucinate. Okay, so hallucination, and thank you for questions. Feel free to interrupt in the middle of questions. I'm very happy is it talk an hour? I'm very happy if I don't get through. Is it?
It's an hour, but you can, we're flexible.
Okay, so I'm happy to take questions as we go. So what makes hallucinations special or surprising maybe is that they're a little different than other types of errors. If you start with perfect training data, and then you do this task, which I'm calling language prediction, some people call it next word prediction, or pre-training, there's a bunch of names for this, but if you had perfect training data with no spelling errors, you'll get a language model which doesn't make spelling errors, and it doesn't make grammar mistakes either. It's really good at those things. And yet somehow it generates these facts which are false, even if your training data only had true statements in it, whatever true means. And okay, so why are we getting these things? And I'll give you a hint of what the theorem says in the talk is that, well, obviously there's some things that have rules, like grammar has a rule that you can distinguish good grammar from bad grammar. You can learn the rules of grammar. Other things like the birthdays of the people in this room, there's no rule, that explains those, and you can't learn that. And those are going to be kinds of things where you're going to hallucinate. So, so we'll get into that. So let's start with that example. Actually, nobody in this room, I assume, knows what my birthday is. Does anyone know what my birthday is? Yeah. You think?
You're the same age as me? I think so.
What'd you say?
I don't want to reveal it, but
Okay.
I think you're the same year as me.
No, not the year, the day. Day and month. I asked the language model if when was Adam Kalai born? If you know, respond with just day and month. So I even said, if you know, I gave it the option to say, if you don't know, you don't have to guess. And I gave it the format and everything, and it comes up with, DeepSeek came up with 3 different guesses, all wrong. As ChatGPT, it came up with 2 different guesses. The third time it was thinking mode, and it said, I don't know. After 1 minute and 26 seconds. Well, it was searching. I have a feeling it was doing a good job searching, and my birthday's not online. So, yay, good job. But this is funny, but it's actually a safety hazard. I mean, even today, somebody could be asking for very, important information that they could use in some high stakes situation, and that could cause them harm. So it's very important that we reduce the hallucination rate as much as possible. Okay, so there's 2 parts to the training language. The first part is called next word prediction. I'm just calling it language prediction because it's not important that it goes 1 word at a time. We're just trying to learn language. We're trying to approximate the distribution of language in our training data. And I'll argue that, yeah, after this first stage, it should hallucinate. I mean, that's the effect of training an approximation of language. And we'll understand more generally what type of errors will have. And then the second stage, though many people think it ends here, but actually it doesn't. There's another stage called post-training, or alignment is what I'll call in this talk. And basically, during the alignment stage, there's many algorithms. It shouldn't hallucinate. This is the stage where we should get rid of the hallucinations, but we're not. And I'll talk about why that's not happening as well. So let's talk about this language prediction task. And let's consider a very simple model where there's a set of valid statements, true, statements, or this actually works for any kind of error you can think of. So you could talk about grammar and spelling. Just suppose there's, just like in binary classification, you have, two sets. You have the valid ones and the errors. Here I give the example of, math formulas. There's a lot more correct statements here that, or incorrect statements in this example than correct statements. So you have two sets, valid and error. In the real world, there's gray area. And in the real world, your training data is going to be noisy. But let's start with this idealized model, and I'll show you you'll hallucinate even in this idealized model. You'll probably hallucinate even more in the real world if the training data is full of noise and edge cases, which are hard to decide. So we're going to assume that there's some true distribution P. The training data are going to be drawn from this true distribution P, and it's all valid. There's no errors in this training distribution. And we're trying to learn from this, from n samples, IID samples from this distribution. We're trying to learn approximation P hat of this distribution. And there's some loss which has been used for decades in language modeling, and it's the same loss. And basically, if these are strings or sequences of text or whatever, you're looking at the negative log probability. You're trying to minimize the log probability, negative log probability of future examples drawn from this same distribution. Okay. And that's the objective of this language prediction, which they call pre-training. That's just
this is a condition on being an error.
No, this is just, so we're assuming all the samples from P are not errors, they're all valid. And then we're trying to learn just, we're just trying to learn a distribution which P hat, which has a low loss, according to this definition. Future samples drawn from this. So we take, if these are all documents on the web, we take a new web page and we ask, what is the probability our language model assigns to this new web page? We want it to be high. And then you can break this down into word by word. You can just say the probability of a document is the sum of the log probabilities, or the product of the probabilities of each word given the previous words. And then, yeah. So you could think of it as next word prediction, but actually it doesn't matter that it's one word at a time or whole document. Okay. And there's many names for this: density estimation, cross entropy. This is a task in unsupervised learning. And for most of the talk, I'll think of there actually not being any prompt. It just generates strings. But this whole thing generalizes to the case where there's a question, like when was Adam born? But that just complicates the notation. Okay, and then kind of the main theory result is a reduction showing that basically if, this prediction task, the task of learning to predict language is harder than the task of learning to classify true versus false or correct versus incorrect. And so, I'm sure many of you remember, obviously from machine learning, we were learning classifiers, trying to separate positive examples from negative examples, and you're given both positives and negatives. Well, in this idealized model of language learning, you're only given positive examples. We're not even seeing any errors. So intuitively, it should be harder because you're learning only from positive examples. Learning only from positive examples should be harder than learning from positive and negative examples. And so we want to say that this unsupervised learning is harder than supervised learning. But what do I mean by harder? I'm saying it's harder. Well, intuitively, it's harder to avoid errors when you're learning only from positive examples. But is it really hard to learn to avoid errors? Can someone give me a language model that doesn't make errors, that doesn't hallucinate?
How is this? I don't know.
It always says, I don't know. That's one good one. Any other ones?
Sorry, what is the learning task again? It should now get a sample and it should say whether it's correct or not.
No, so now it gets a sample and it has to generate another example similar from a similar distribution. Thank you for asking that. So yeah, so the task, what you described is what I'm calling the validity classification test. That's the binary classification. You're given some positive and negative examples, and here the task is classifying. Here the task is generating a new sample, trying to be from the same distribution.
If it generates only training data.
Exactly, that's another good one. So maybe it should just memorize the training data and only generate samples like, repeat the same facts that it saw in the training data. Okay, that's another option. So what I'm claiming is not, I need to qualify it, right? I need to make some assumption in order to make that true. But what the takeaway that we'll get is that basically the models, these predictive models, will hallucinate wherever they can't really distinguish. If you can't distinguish correct from incorrect, I'm going to argue that the pre-training process, this language prediction task, will actually lead to hallucination. It won't generate one of those two nice language models that you guys
don't allow it to say I don't know in this.
It is allowed. I don't know is valid, and maybe 10% of the training data is full of I don't knows.
Okay.
So good, great question.
So when you say only positive, you mean also some zeros, like this I don't know?
Yeah, let's assume that I don't know is valid. So it's in the set of valid, and I'm not assuming it's a uniform distribution on valid. So it could have 10%, as much percent as you want, of I don't knows in the training data.
So the statement that prediction is harder than classification, you mean you can take a machine that can generate X-token prediction and use that to classify?
Exactly. So you guys told me why it's not true, but that's exactly the theorem. So the theorem says if this training distribution assigns probability 1 to the valid set, so P of V is 1, it's all the samples are that. Then for any other distribution P hat, okay, I'm going to do what Elad said, and I'm going to use that P hat to classify. So I'm going to say this thing on the left here is the hallucination probability is at least twice the classification probability minus some small terms. And I need to define and unpack these terms. So this is the probability that if we generate a new sample from our language model, P hat, that it's not going to be in the valid side, it's an error. Okay. And that's what we call hallucination intuitively. So we've got our language model approximation. This, on the other side, is the probability of screwing up on this classification task, which is something valid or an error? And I have to even tell you what the classifier is in the distribution. So the distribution that we're trying to learn on, it's a binary classification task. Half the time it's going to be a random positive example from the distribution P of training examples. That makes sense. We have the true distribution P. We assumed it's all valid, so we'll have positive examples from that. And half the time it's going to be, this means a uniformly random error. So half the time we're going to take a uniform sample from the error set, okay, and we'll call that negative. So that's our classification distribution. Makes sense, I guess. And then we're going to look at the probability. We're going to repurpose, as Elad suggested, we're going to repurpose our language model to be a classifier. We're going to take our language model and we're going to see whether it's bigger than some threshold. It turns out to be 1 over the number of errors, okay? And that's going to be our classifier. And whatever error rate that classifier has, our hallucination rate is going to be at least like twice that. So if it's minus some terms, which I'll try to argue are small. So if this task is really hard to learn, like birthdays, you'll never learn birthdays. I'll tell you the birthdays of people on the left half side of the room. It's not going to learn the birthdays, the people on the right half side of the room. It's a really hard classification task. Then you have error rate like close to half. Then your hallucination rate will be close to 100%. Yes.
Okay, something maybe a silly question, but in the whole training process, you're thinking about only giving examples from Z, and we're not even referring to E in any way.
Right.
So like I can have some E1, which are maybe errors, and maybe this is like in a bigger space thing that have more error. Maybe, I don't know, just
Right.
gibberish.
Right.
And so, but the probability that you're talking about in the right-hand side, at least a priori, seems to depend on a set that the model hasn't even seen. Like, so why?
Right. This is a hypothetical bound. So it's saying if there is a set E, and by the way, in our paper, we talk about a gibberish set. We have a third set gibberish because yeah, what we're saying is if there is a set E, which you can't distinguish from the valid ones, then you should generate stuff as if it's coming from that set E as well.
So it's like worst case over.
Yes, this holds for every, this holds, sorry, I didn't say, but this holds for every V and E. Right, thank you.
1/E should be very tiny, right?
Yes, exactly.
So then P is the number with a non-negative number.
Yeah, but V is the number valid, and so are you asking about this term? Yeah.
But also the 1/E.
Oh yeah, 1/E should be tiny. So if you think about, you know, facts or statements, birthdays, you know, there's millions and billions of people. So this would be like, you know, 1 in 365 billion. I don't know, because the number of each person has, you know, 364 birthdays that they weren't born on. So there's a lot of errors there. But yeah, this is a tiny number, but this is how we're thresholding our language model. We're going to take some tiny threshold, and that's how we'll do it. And then this term here, thinking about the ratio of the valid to errors, in many applications, there's way more errors than valid. Like each person has 364 days that they weren't born. And, you know, the language model can hallucinate about all kinds of things that don't exist. There's a lot more errors in many cases than correct things. So whenever that's the case, this term will be very small. And then this last term, of course, is hiding all the work of the theorem, which is, you know, saying, why does the language model not say, I don't know all the time? Why does it not just regurgitate the training data like you suggested? Could do either of those and it wouldn't hallucinate. Why is this term small? So, and those language models will turn out to have a big term here. And this term is what is called calibration. So it's a predictor, it's trying to make predictions. And we need to say, what is a good prediction? What is a good predictor? And so this term is measuring how calibrated it is. And what does this mean? So this is the set of things which are likely under your language model. They're heavy hitters. They're more likely than 1/E. And so this heavy hitter set, we're saying that the language model should approximate its probability. So there's a true probability of generating stuff in this set, and then there's the language model's probability of generating stuff in this set. And you can estimate both of these because you can say, you know, okay, let's draw samples from the language model and see what fraction of them we can compute p hat of x and see what fraction of them are bigger than 1/E. And we can take samples from the training or test distribution, whatever, p, the true target distribution p, and we can see what fraction of them are bigger. And it's saying these two things will be close to each other. And so that's where we're saying, that's what this, the whole language model learning, you know, why should it get a small quantity here? So that's the last thing that I need to argue. So this is basically a phenomenon that is known empirically and in the calibration literature. So this is a plot empirically showing that language models, when they say something has a certain probability, that it tends to be that often true. And mathematically, you can also kind of make a physics style hand wavy argument why this is true, which says that, you know, well, if your loss wasn't calibrated, this thing was big, we could actually do better at that loss that I mentioned at the beginning. Remember, the goal of this thing is to minimize this loss. So what we think about is, imagine rescaling the loss. Imagine taking your language model and rescaling it by some factor 1 plus alpha on the heavy hitters. And if it's not super important you understand this, but the intuition is, yeah, if you were miscalibrated, you could reduce your loss. And so I don't go through the math here, but the derivative, this miscalibration turns out to be exactly the derivative of this rescaling loss when you don't rescale.
So is this something that's actually done? Like that you'll train your model initially, then change the loss function and try to calibrate?
They would. If this helped, they would do it, but they don't need to because they just do gradient descent. And empirically, gradient descent works really well at minimizing the function. If it turned out to be not calibrated, then you could use this trick to further reduce the loss, but you don't need to because empirically it turns out to just the process of gradient descent, which is directly minimizing the loss, tends to get calibrated language model in the first place.
But here, because like 1/E is like so small, should we like do it without calibrated to that level?
Well, we don't need good question. We don't need the probability. We don't need this term to be less than 1/E. It's this set. The set is defined by the things which are bigger or smaller than 1 over E. And this set could be empty. This set could be the whole thing. It's actually, calibration sounds like an impressive term, but actually it's really easy to be calibrated. The uniform distribution overall over any set is calibrated over the whole set of valid and errors. Good question.
Actually, I find myself confused. If you know how to estimate this set, don't you know how to avoid the hallucination part?
Well, this set is defined in terms of your language model, which is a little weird, right? So you're kind of looking for a fixed point here in some sense. You know, you're looking for a set, but that's what I'm saying.
If it was P instead of P hat, then what I said would be, then you'd.
Right, but then you'd have to, we don't know how to compute P on any point.
Right.
So, but if you knew, if this was some kind of goal and you had it, yeah, then it'd be really easy to avoid. But calibration, as I'm saying, is actually not a hard thing to achieve. I mean, the uniform distribution is calibrated. So calibration on its own is not hard. It's just the term we need for our analysis to show that, you know, that it's just something that we need to show is small. And basically the language model that always says, I don't know, we need to rule that out because it doesn't hallucinate. And that language model is not a very good, it's not a calibrated language model. So what we're saying is that during this first stage of training a language model, we were trying to get a predictive model, you know, that we are basically doing well, and we're going to get a low calibration error.
How much does the theorem depend on the loss function?
Good question. So I don't know if other loss functions would give you, I think many loss functions, if you're trying to model the distribution, should give you a calibrated prediction. It's kind of a natural term. I think there's like squared error and other things also give you a calibrated, typically give calibration. But it so happens that this loss function is the loss function that's been used for decades. Pretty much in pre-training. Maybe people tweak it. Maybe in DeepMind they have a lot can tell us if they use something else. But
well, the one thing you could do, I think this will give the same result. You can take before you do the you move from the embedding to the actual word. You can do L2 kind of Euclidean loss minimization of these things. That's the distribution of your words, right? So I think it's the same thing. If you optimize the distribution.
Right.
Then you probably will get the calibrated forecast out.
Yeah. So back to the many, it's a great question. There's papers written that basically their title is all kinds of prediction losses lead to calibration. So we cite one of those in our paper.
So Adam, like let's say I believe this is like reflecting the empirical phenomena. Like, let's say I want to now make a model which does not hallucinate. Like, what should I do? Should I break T of equals 1, or should I break?
Well, that's going to be the alignment stage that I talked about, the next stage. But this is a stage where we take tons of training data and just try to learn language. And then we want to use alignment to get rid of the hallucinations. So that's a good lead-in. But before I do that, I'll just mention, yes, this holds for any language model. It doesn't matter that it's a neural network or an expert prediction. It's as long as it's got some reasonable loss. And the uniform distribution, as I said, is calibrated. And the next stage, which is after the alignment or post-training, typically gives you an uncalibrated model, miscalibrated model, but hopefully which hallucinates less. And it does hallucinate less. But there's still like a conceptual message here, which might be helpful because there's been a lot of studies of hallucinations and a lot of mystery, and many of them are basically picking up some phenomenon, which I think is true. But basically, what I want to say is that all the reasons we have for errors in binary classification, you know, when we used to do binary classification of cat and dog or whatever, we would have some errors. And then depending on the task, we might have some errors, we might not. And we understood the reasons why you would have errors. And all those same reasons, I claim, port over. So sometimes you didn't have errors, like spelling, maybe there's some rules, or grammar, there's some rules, and you learn those rules, and your classifier is perfect. Sometimes when there's a high VC dimension, for those of you who know it is, like a statistically unlearnable class, there's no pattern in the birthdays, then, you're going to get a lot of errors. And those, birthdays are a good example of something where, even you can't learn to distinguish valid examples from errors. And even it could have, I don't know, in the valid examples, somebody somebody asked you a birthday, you could say, I don't know this. Of course, if your entire training data was I don't know, you would learn that really well and you wouldn't make any mistakes. But as long as some of your data is not, you're in trouble. That's one type. And there's other types of errors. Like sometimes, you're learning a circle, but your classifier is a line. So when your classifier is not well suited for the task at hand, then you also fail. And this is an example, I would argue. So if somebody asks you how many D's are in the word ladder, the way a language model represents a word is not by letters, but it breaks it down into tokens. And each token is some, sequence of letters. So it has to learn that this DER token, which is 19975 or something, has one D. So it's a hard learning test. It's a bad representation for letter counting. So all these reasons you have for errors in binary classification port over there. And then the last thing I want to say before we move to fixing the problem is you can use this also to estimate the rates of hallucinations, okay, for different types, and used to do to this good Turing estimator, or Alan Turing's estimator. So Alan Turing, of course, wasn't thinking about hallucinations at the time, but he was thinking, I think about, I don't know, here are examples like fishing. You go fishing, you catch 100 fish, 50 of them are salmon, 20 of them are tuna, whatever. And you're asking the question, if I go and catch one more fish, what's the chance that it's kind of fish I've seen before or a new fish? And the estimate is you look at how many types of fish appeared exactly once. Intuitively, every fish that appeared once, if you think of that like a leave one out sample, that's like as if you had gone fishing one more time, and was that a new fish? So we're going to use that. So we're going to think of like the birthday setting where you have no pattern. Let's say there's just one correct answer for each question, but you could also have, I don't know. It could be I don't know, and the training data could have I don't know. So you have one correct answer, but you also have the option to say I don't know. Now we'll have questions and answers, not just statements. And there could be celebrities like Avi or Einstein who, I'm sure your birthday, I checked, your birthday's on Google, it's, can't hide, my birthday's not. You get n samples from the distribution, and then our estimate is the number of facts, not I don't know, but number of true facts appearing in the training data that appeared exactly once. And that's our estimate, that's gonna be our lower bound on the hallucination rate. So we're gonna say the hallucination rate is at least the fraction of facts in the training data which appeared at exactly once divided by n.
What does it mean exactly once? You mean that it's never, if you see X was born in this place and then X was born in another date?
Well, we're going to assume that they're the perfect training data, which means
what does it mean facts that appear exactly?
So exactly. So and let's assume there's perfect training data, which means everything's correct, and there's even, make life simple, there's even only one way to say any fact. Okay. So then there's just a set of facts. And the training data has some facts more often than others. Okay. Some facts, it's a distribution, some facts are highly likely, other facts. And then we look at our training data and we see how many facts appear exactly once, uniquely. Okay.
I still don't understand I thought if it's correct, it appears exactly once. But everything appears exactly once, but with different orbits.
No, but like my birthday doesn't appear on the web at all in our training data. Your birthday might appear 10 times.
You have to know the size of the population.
Yeah, but this is just a conceptual bound. It's saying whatever that rate is. So I can't implement this. I mean, I guess I could try to go over the training data, but the real training data is messy and it's not perfectly clean, and there are many ways to say things. But it's sort of a conceptual thing. If you imagine, but we can still kind of use this to think of toy examples. And if you think, okay, so country capitals, do you think who thinks the country capitals appear many times just once, and who thinks they don't appear just once? If you look at the country capitals in the training data.
Here a lot, many times.
Many times. There'd be very few that would appear once. Birthdays, you're going to have a mix. Some people are celebrities. Their birthday is going to appear many times. Others may never appear or appear just once. Okay. What about article titles, paper titles? You think that many paper titles, if you were to go look at random paper titles in the training data, they appear just once, or they appear many times? Yeah. What do you think? So I get different opinions, but I agree with a lot that I think when I publish a paper, even if it's rejected, it's on my webpage, it's on my CV, and I put it in archive, I put it everywhere I can, I go talk about it. So I think most of them appear many times, and the reason that we're hallucinating is actually not because of the not because of this phenomenon, but because of the bad representation. There'd be a better way to represent paper titles, not a neural network, but use a database, a list, store the paper titles in a list. And then when it came time to generate from that. So neural networks are not a great way to represent and learn article titles. And therefore, this is a lower bound. You can hallucinate more. Are there any questions? A small term here is the same term that we had on the previous bound.
Oh, why is this a corollary?
Good question. So now let's go back to our theorem. So yeah, I mean, there's a little bit of work to do there. So we have to, we basically have to argue that you wouldn't be able to classify. So the rate of new stuff, whatever new stuff you haven't seen, in this model, we're assuming that there's no way to learn it. We've assumed that there's no connection between any examples, they're independent. So your birthday is independent from my birthday. So if there was, if there was a 20% chance we're going to get a person with a new birthday, then the classification error is going to be 20%. So that's what. It's a kind of easy theorem. And then the only work that takes a few pages is to make it high probability. But the expected bound actually follows almost immediately.
Why do we lose the factor of 2, or does it not matter?
Oh, well, the error, it's because these are great questions. You guys are asking great questions. So yeah, so if there was a 20% chance of getting somebody new, but then the distribution is half-half. So kind of, it gets downweighted by half and then upweighted by 2. Yeah, people never ask these questions. Most times when I give the talk, they're not as interested in the first part. They're more interested in the second part, which doesn't have as much theory, but is more intuitive. So, so for the first part, we talked about, even if we took noiseless data and we trained a predictor for language, we should get these hallucinations at some rate. And the intuition, you can even think about it in terms of, basically, have you ever seen like your email, some kind of predictive email, right? I mean, intuitively, you're getting predictions. What do you expect? Somebody asks you what your birthday is. If you're typing on the phone and it gives you a suggestion, you say, good suggestion, right? That seems reasonable. Yeah, nobody expected it to be right. Somehow when you change the form into a language model, everyone gets upset and says, wait, this is a hallucination. It's like here, of course, it's a good guess. Here, it's a hallucination. So there's kind of a picture you can draw to explain that intuitively. Now, the second part of language model learning is alignment or post-training. And here there's many different algorithms, okay? So I don't have time in the talk to do theory of all these algorithms, and moreover, I don't know all of them, but I couldn't. So I'm going to try to abstract a layer and explain why we're still hallucinating. This should get rid of the hallucinations, and it's working. It does reduce a lot, but why is it not getting rid of all the hallucinations? And I'll give a simple analogy to a multiple choice test. So I said that you guys don't hallucinate, but actually probably all of you have. When you took a test, I mean, how many people here, when you take a test and they ask a question and you don't know the answer, how many of you write in, I don't know, or you leave it blank? Almost nobody, right? So we want the language models to say, I don't know, or express uncertainty, but we're evaluating them according to some metrics that are usually some kind of, correct or incorrect test where you basically get no points for saying, I don't know. So think about it. If somebody had a language model which didn't hallucinate, a better one, it'll do worse on these tests because it'll actually, it's better. It's a dominant strategy to guess when you're unsure. So so the team, there's a whole team of doing this alignment, and they're trying different stuff. And when they hit on one thing and maybe it doesn't hallucinate, it looks worse under the tests.
So what is the objective in the post-training?
Usually they have a bunch of evals and they look at these evals and see how well it's doing. They're not optimizing an objective. Unfortunately, there's many techniques, so I can't even say what it is. But, when it comes time to choose one, they have to decide. They look at evals, they look at other, they talk to it, and they have many ways to evaluate it. Another way they have to evaluate is they show it to humans. They can show 2 model outputs to humans and say, which one do you like better? Turns out people like hallucinations, usually because they don't know that it's hallucination. You show it a question, what does PGGB stand for? You give it the 2 answers. One says, I don't know. The other says, these things, people love the bullet points. And so many of the evaluations are favoring the hallucinations.
This seems easy to fix.
Yes. What's the fix?
To favor I don't know when they don't know.
Exactly.
Penalize wrong answers.
Penalize wrong answers. So great. So you're also exactly. So I'll just jump through this. So the score, if the score is I don't know is the same as wrong, it's a dominant strategy to guess. And there's many papers, by the way, that talk about some of the ideas you just mentioned that reduce hallucinations. But the reality is they're not being used in industry for the reason that I think all of you get, which is that in most of the benchmarks, if you take look at some evals and public evals that everyone uses, humanities last exam, GPQA Diamond, Amy math tests, they use a lot of math tests, software engineering benchmarks, they all have the property, some of them are multiple choice, some of them aren't, but they all have the property that saying I don't know is it's like wrong. And so you're better off hallucinating. So the suggestion, which you guys are going for, but there's a subtle point here. First of all, let's not add one evaluation for hallucination. Let's change the way we're grading all the existing evaluations. Why? Because if you just add one evaluation, there's literally hundreds of evaluations that are used for language models. So now these hundreds of evaluations are all encouraging hallucinations, and we have our one little, evaluation. So instead, it's better to regrade, to change your grading system so that it encourages appropriately expressing uncertainty, like we talked about on the first slide. That's the goal. We want it to say, I don't know, or whatever the appropriate way to express uncertainty is. But now I'm going to challenge you. I love your idea of, penalizing errors, or rewarding, I don't know. But what's the right way? I mean, when should you say, I don't know? When shouldn't you? What's the threshold? How can we compare all these language models in a fair way? If we just created an eval and I said, well, I think this is the right time to say, I don't know. And somebody else said, oh, I think the penalty should be 3. You say the penalty should be 10, and you say the penalty.
And in particular, you can request the LLM to give you a source.
To give a source. That's
I assume this was being done.
That's done. That's some of the in some of these evals. That's one of the ideas. It's going to be tricky to regrade all of these existing evals, like the Amy, the math test, and you can't always give us for math. You don't need a source; it's an idea, right? But it's a good idea, and it's one of the ideas.
You have the model output a probability, and then use like a real value.
So that's one idea that's used a lot. But I'm going to turn it around and propose. And let me just propose that we tell the language. This is kind of an obvious idea. We'll tell the language model what the penalty is. And I know it sounds funny, but nobody did that before. They proposed the idea of having penalties, but they didn't tell the language model what the penalty was. So it was like I gave you a test and I said, there's going to be a penalty if you get it wrong. So you can leave it blank. But I'm not telling you what the penalty is, or there might be a penalty. It might be no penalty. How annoying would that be, right? And then we wouldn't be able to compare. And then Elad would say, no, I did better. And, Elite would say, no, I did better, because they would have different thresholds in mind, different penalties in mind. So if you state the penalty in the question and you say, you're going to lose 3 points for each incorrect, and you're going to get 1 point for correct, and say 0 points for no answer, and then there's going to be, you can back out the probability that you should answer if you're more than 75% confident and whatever. So you can choose this this penalty however you want. And in fact, for any penalty, it's a reasonable and fair comparison, and you could do it across many penalties. And you just compute this term. So the second point is, if you can just, this is one way to properly, according to proper grading system, grade appropriate indications of uncertainty. But in general, the whole idea of appropriately indicating uncertainty is a tricky thing to grade. But if somebody tells you, look, you have 3 choices, 2 choices, give an answer or say, I don't know, then it's easy to grade. So this is a system that you could apply to all the old evals. At IAS, I did it, and I feel funny talking about empirical, but I did some experiments, and as you increase this threshold, how confident you have to be, sure enough, the language model abstains more and more across different language models. So if I say if I increase the penalty, then it should more and more often say, I don't know. Okay, makes sense. So that kind of works. But if you actually look at, instead of looking at the abstention rate, if you look at the rate of the score, which is the correct minus the penalty, and as you increase the penalty, or increase the confidence threshold that's equivalent, it actually drops below the I don't know threshold. So at some point, the language model would get a higher score in the test by just saying I don't know all the time. So it's overconfident. And okay, so this is still an idea though that I think is reasonable because it's an objective way to score things, and it's a way to score appropriately indicating uncertainty. It helps with the property that language model scores these days are so high that we all get a perfect, they're all near 100, so you can't even tell the difference between them, because then, when you start looking at these penalties, the scores get separated. And, there's another interesting notion that you can consider called calibration here, but it's the reverse. Calibration usually is about a prediction. If I gave a number, one of you recommended giving a number afterwards, right? Like maybe it should, so it's like a forecast or probability prediction. Here, I'm turning it around. Instead of asking you to make a prediction, I'm going to tell you the threshold, and you have to be calibrated to that threshold. So I did it in this experiment. I said, I'm going to lie to the language model. I'm not going to tell it the true penalty. I'm going to tell it the best penalty, which will give it the best score. So I can tell it, yeah, you'll be penalized 1 million if you get it wrong, or 1 billion, or whatever. And for each threshold, and then you can see the scores go up when I recalibrate after the fact, and I lie to the language model about, and we all have this, sometimes we lie to ourselves. So this behavioral calibration is kind of a way to quantify one aspect of appropriately expressing uncertainty. So many of you have heard of calibration in terms of this notion of David, which is like, if among a predictor that says, let's say your flight's going to be 20 minutes late, or whatever, however late, you look at averaged over those times where it says 20 minutes late, on average, it should be 20 minutes late. And if it was only 5 minutes on average, it's not calibrated. Here, this notion of behavioral calibration is more like lying to somebody. So some people, my dad gave this example, some people set their watch ahead 10 minutes. Why? Why do they lie to themselves? Because it's better for their utility. They're happier. Their performance improves when they're lied to. And the language models have this property that if you tell them that there's a bigger penalty right now than there is, their performance goes up. And you would like them to learn not to be that way, so that people could tell them how important something is, and then they would adjust their guessing rate to that threshold. Okay. Any questions on this? So, okay, so and that happens in the language models. So looking forward, I hope that the reduction in hallucinations will continue. We shouldn't wait for accuracy to hit 100%. It will never do that, because there's always questions that are unanswered. So we should we should focus on the error rate, not on the accuracy rate. And there are better ways to express uncertainty than just, I don't know. Okay, I looked for it online. I spent 1 minute, like when the language model said, I don't know about my birthday, and thought for a minute, kind of annoying. If it had said, I searched, all these websites and I didn't find any public information, maybe that would be a better way. Or maybe it has some information to guess. I would guess that he was born in the fall because of this or that. I remember asking about the left-handed or right-handed, and it was saying whether I was left-handed or right-handed, and it actually like kind of watched some video that I'd given. It's like, well, look how he's holding, talking, maybe he's right-handed, and it was a good guess. But explaining the source the reasoning would be obviously better. So that's the future. But the current problem is that these language models hallucinate, and we need to, stop that right away. And then ideally we'll get to this point where we can have linguistic calibration. One thing I want to say is that, this super intelligence thing, I'm talking kind of about a problem we're facing today. But this morning, Avi and I were talking about, what happens when the AI gets way smarter than us? It's a whole new can of worms. Hallucinations are still important. Fairness is important. All these things are important. But there's so many things that we don't have definitions for, notions for, even reductions. Things change when you have this whole time. You spend you spend so much compute on a training set of problems. We don't think about that much in complexity, but it's not that the problem is defined. You need to find the shortest path for all graphs. It's that I'll give you a bunch of training graphs. You can spend forever getting good at this problem. And then so you get a huge amount of time in pre-processing with some examples. And now now what happens when we do that, and how do reductions work? Now here, if you get really good at one problem, are you good at another? There's a lot of really interesting problems here. And I think a lot of people are studying AI as biology. It's important, sort of a social phenomenon, and let's observe it and see what's happening, and we'll document it, and kind of like an organism that's growing, evolving out of our control. But I would argue that there's room for another study, which is, I think of it as like AI as cryptography. So the things like RSA and the blockchain, they came out of nowhere, but they're things we engineer, we build. And we can build those, however we want, and we can make them very secure. And cryptography is really about making something secure against an adversary who has more compute and more intelligence than you. And so, things like RSA may be secure even against the superintelligence in the blockchain. And so I think this is a really promising field. I mean, I have a minute, and I wanted to, is that okay if I
Please.
Show a quick result like on the blackboard?
Yeah.
Okay. Should I do it? Which side should I do it? Is there any
We
easy
can
way?
lift if you're done.
Yeah, I'm done. I have one. I'll do this slide and then I'm done. So the analogy to humans is that with language models is that humans have two language models in their head. This is a cheat, but are there any biologists in the room? Yes, I can cheat. No neuroscientists. All right, so the one in the back is close to the ear, and it's called Wernicke's areas for listening or predicting. And it needs to hear a lot of things that are maybe. Is this your birthday? No.
No.
See, humans, we learn not to hallucinate because we look like morons if we do. We don't need it on our tests because if we hallucinate, we learn outside the test. Okay, but anyway, it hears a lot of things that it knows not to be true. Okay, or it doesn't know whether it's true or not. A predictive one, and some things it knows are true. It might even see some swears and offensive things. You want your ear needs to be able to understand things that you don't want to produce, and then you have a totally separate language model. There's a condition where people generate actually from this part of the brain. It's called Wernicke's aphasia, and they babble, and it's like hallucination. But then we want the mouth, the generative part, to be the part that says, what we want. And the big question of alignment is what do we want it to say? And it's kind of the challenge that is open for everyone. And you don't need to know a lot about how language models work today to answer this question, because it's a big open question. Look, what is it that we want? We get to control these language models, hopefully. What is it that we want them to say? I mean, we have ideas, there's some starting points, but I think this is a great time for theory before we're there to, outline and define what the goals should be.
So, I mean, the issue you're raising is that when we do prediction, next token prediction,
right.
The reason we hallucinate is that the optimal predictor, in some sense, have this good Turing estimator.
Right.
Do you think that this goal maybe would be corrected in the pre-training itself, like in the loss function itself, next token has something else that doesn't.
Possible.
Is there such a thing in?
There probably are a couple papers on that, but I don't know. I haven't seen anything very compelling on that, but it's possible. It's a good question.
Yeah, I mean.
In some sense, though, I'd argue it's not just a statistical thing. I wonder if I pull this out, will it just go out? No. Okay. But in some sense, I would argue that's not pre-training is not the right time, and I'll tell you why. Because there are times you want hallucinations. Like you ask for a short story, you ask for a recipe. It's fine. I do want it to make up a recipe for me. Sure, I tell you the ingredients I have in my kitchen. Go ahead and make it up. But birthdays, I don't want you to make up. So really, it's a delicate balancing act that we need to teach the language model. Go ahead and guess here. Don't guess here. Be extra careful here. And so I feel like it's more of an instructive process that we need to, then you could just determine maybe from the training data.
But I mean, it learns a lot of things automatically, and humans know how to hallucinate.
Yeah, maybe it could figure that out from the training data. It's a really good question.
Why doesn't it figure it out?
I don't know. Oh.
I mean,
Well, it's trained because the training objective that we're using is the same one that would predict the next word on your keyboard. So that objective, it doesn't know that it's language for that one, but maybe we need to change the objective. I don't have an answer. I mean, maybe changing the objective.
I mean, there is a context, even in pre-training, that you should know if you're in an exam or you are, talking in front of your peers or something.
Yeah,
like that.
exactly.
and then you can change the.
Yeah. So maybe it could almost be done through prompting in some sense, where you say the question is this, and then we ask the careful assistant, and maybe you would hope at that point that.
And also, it would be embarrassing
Yeah.
if you come up with the wrong answer.
Yes, and you'll be embarrassed and fired if you get the wrong answer. And there's a paper showing if you offer the language model $20, better. So let me show you this a glimpse into some idea for cryptography. It's a very simple theorem. I can write it on one thing. Should I write on this cool blue one? Okay. Yeah. Let's see. All right. So here we're just going to generalize, and we're going to. It's kind of like a boosting approach. We're going to assume that we have k distributions. These are distributions over strings. Okay. So these are just distributions over some set. So these are distributions, some set X, and then so we're going to assume that a majority. This is I was trying to read this paper of Avi this morning. We're going to assume that a majority of these are good distributions. Okay, so there could be. We don't know. Some adversary could have corrupted a minority of them, but we don't know which ones. And so we're going to define the median distribution. So of course, you could look at, the average of these distributions over some, you could just consider the average distribution, but that'd be just like generating from a random language model. You'd have maybe 50% chance of being good. But the median distribution is going to be proportional to the median. So I'm going to define a median distribution, which on any point X is proportional to the median of these numbers.
And you normalize it.
Yes, you normalize it. So I tried to write proportional here. So we divide by the sum of the probabilities. The medians. If the median is always 0, then it's not defined. But okay, so this is the median distribution. And then it has this very simple property, which is the theorem is, it's not hard to show, that, okay, so I'm going to say for any think of some unsafe set. We don't even know what it is. There's some set of X's which are bad. Call them U, unsafe. There's some set of unsafe. We don't know what it is. Okay. And for any set of size, these are going to be safe models. So the good ones, the size of the set is so this is a set of indices, and it's got to be bigger than k over 2. So majority of the models are safe. So if a majority of the models are safe, then the probability that the median distribution assigns to this unsafe set is less than some term here, which I'll define in a second, called the overlap, times the sum of the probabilities of the safe models of this set, the safe models assigned to the unsafe distribution. Okay, so it's a very simple theorem. It says that the median probability will be some amplification of the safe model's probability. So these safe models hopefully have a really low probability. This could be any kind of unsafe thing. Maybe you're thinking the language model on its own, you'll ask it to write a program and it'll inject some code vulnerability or some awful thing, some evil thing that you really don't expect a safe model to do. That's called like a misaligned AI that it went off and did that. So you expect exponentially low probability on the safe models, but maybe the unsafe ones, who knows? And it could be impossible to detect just from looking at it. So this gives you this approach, and then the definition of this term here, this is a bit of a problem for current language models, but maybe it could be improved. And I would love it if someone in this room could do it. It's basically you sum over all points in your set X of the minimum of the safe models probabilities. Okay. So this is the overlap. So if there were just two models, it's basically you kind of are looking at the overlap. If it's two models, it's 1 minus the statistical distance between the distributions. But in general, for K models. So if two models, you want to know how much they overlap. If they're identical, this is 1. If they're disjoint, this is 0, and that's what it is. And so this is just kind of a very simple thing. And we have I forgot to say, my wife will kill me because she's a co-author. So this is with Yael Talman Kalai. So there's 2 Talman Kalais. Or Zamir. Sorry. And we have basically, we take this and we get some efficient algorithms. So this is kind of an abstract algorithm, and who could normalize this and stuff. But we have in the paper like an efficient algorithm. This is, just the beginning. This is not guaranteeing security or anything, but I love it if like people can have better ideas. There's a lot to do. This is actually inspired by work of Nikhil Nyas, Shyam Kakade, and Boaz Barak, where they do something like this for copyright protection. But in general, I don't know. I mean, I feel like there's a lot of open questions in this field and definitions that need to be made. And so I'm trying to I'd love to work with people here at Theory questions. And I think there's a lot of opportunities. So I'll stop because my time's up. But thanks for inviting me.
Some questions?
Is there some way you can try to enforce this, reduce hallucinations by checking if your answer is stable? Because when you ask for the birthday, you got multiple answers.
Exactly.
So you can say it's wrong, right?
Yes, that's one of the approaches in that huge list of papers. It's a good idea. Because you're saying, yeah, look, it gave 3 different birthdays. Come on. Yeah.
Doesn't work so well though? Or?
It does, but that's what I'm saying. People, in the companies might be disregarding some of those good ideas because it doesn't necessarily improve their current benchmark performance. It might be expensive. You need to make it efficient and practical too. So, but there's
that's the thing to answer the question 10 times each question.
Yeah, I think it might be a good idea. I mean, some of the papers have shown that reduces hallucinations.
I was wondering on this, this is, I guess, a specific question about this setup, but do you have a feeling how necessary this delta S determinant? Is there some toy models where it's necessary?
Yeah.
Are there connections? Also, it feels like with robust statistics or something.
Yeah. So first of all, I should say that this is unfortunately going to be a tiny number for current language models. Like if you train 2 language models, if you take, the Gemini Pro language model from Google and you take our language model, it could be exponentially small. So it's very bad. And so great to improve this. I don't know. It's inherent to the way we're analyzing it, but maybe there's better ways.
There's no statistical bound or something. Currently, it says there's not some better predictor.
I mean, if you just define the problem in this way, I don't know. It's a good question because if you have 3 language models that
if you
have a tiny overlap, you're kind of the intuition behind the algorithm is you sample from the median, you sample from the overlap. If you have 3 algorithms that are three things that overlap and one of them is bad, then basically, if you start with 2 safe ones that have basically, almost a tiny bit overlap, then they also have some probability of generating harmful, unsafe outputs. And for all you know,
oh sure, they're all
they could be in here. So that's the intuition.
What can you say why the overlap kind of appears in the theorem?
Why it appears?
Yeah,
because our algorithm is basically sampling from the overlap region. So what we want is our 2 safe. If our let's say we have three models.
Which algorithm are we talking about?
The median sampling algorithm, the median distribution. So the median, intuitively, if you have 3 language models, then the median, the median is going to be kind of the overlap. Okay. And now we're assuming that this is, let's say, the adversary, right? And the adversary could intersect with so the adversary, if they're smart, they'll put all their weight on the bad ones, the unsafe. So this is the adversary should kind of try to, maybe it doesn't matter what it does else, but the unsafe region should be here. It should put all its weights on the unsafe. And now this part here is kind of assuming that the language models have a small weight, they're safe. So they have a small probability of being unsafe. Of course, if they have a big probability of being unsafe, nothing goes. But assuming they have a small, so this is really a small region. This is the, let's call that the U.
Sorry, this is you. Oh,
Yeah, exactly. That's the U. U may also extend out here. I don't know, but let's say it, the adversary will put all its weight inside there, and then so you need the overlap to be bigger than the unsafe intersection of the unsafe for the models.
But I mean, it's surprising, it stands to reason the two models would have much larger overlap, maybe if you measure it differently.
Yeah, or there's actually like a potential approach. This is kind of a canonical thing. Like if you ask if the question is, what is 2 to the power of 50? There's only one answer. So it's kind of safe. If you take 3 models, you take the majority. Now, if you prove this theorem, well, there's millions of ways to prove a theorem or write a program. There's millions of programs. If we could come up with a canonical way to write programs to kind of encourage them out. So if you say like, here's the right distribution, take one of our smaller models like GPT-4. It doesn't write good programs. But let's take the distribution of programs output by GPT-4, conditioned on it being a good program for whatever task. That's a well-defined distribution. We can all aim for that maybe, or something like that to try to get us, because otherwise there's stylistic differences and things that might make the models. So there's some kind of canonicalization, and maybe some kind of canonical approach for safety would help. I feel bad because I'm over time, but you say it's okay, but yeah, okay. But I have time, yeah, so keep over there. Is there a question?
Any more questions?
Yeah. Oh, sorry, you go ahead, you have this as well.
Yeah, actually, this was connected to Peter's last question. Like you're saying that there are a lot of theoretical kind of approaches to solution, but this is like less happening in practice. You also said maybe it's not, it's a challenge to make it sufficient and so on, but like, so what is the challenge? Like why aren't we using, like, what should be the correct approach so that they actually be?
I'm pretty much believing what I'm saying, that these other empirical approaches, they're empirical, they're not theoretical approaches, but these other empirical approaches, they write papers, they show empirically it reduces hallucinations. And I think that, to get adoption, you need the people who are choosing which approach to use to be paying attention, to have some reasonable way to pay attention to hallucinations. And right now, they're looking at a lot of evaluations which, benefit from hallucinations. And then maybe they have 1 or 2 that, some hallucination evals that somebody wrote, but they're now facing this decision with, I've got my dozens of evals that I'm really good at. And now you're telling me I shouldn't guess on this multiple choice test or, whatever. It's effectively that.
Sure, but I guess people that make these decisions, and they probably heard this argument or aware of it, right? Like why isn't this being abandoned? Like,
they have a lot to balance. There's so much going on, and a lot of it is safety related. People there's self-harm. There's like so many, they have so many factors and things to balance. And hallucinations are one of them, but they may not be the priority. Plus, they're always trying to improve their accuracy. And for a long time, accuracy was improving dramatically. Like it was, they were getting basic math questions wrong for the beginning. So maybe my hope is now that, hopefully we'll start peaking. So they were reducing hallucinations just by increasing accuracy before. So my hope is that now that, hopefully things will plateau in terms of accuracy at some point, you can't get more accurate because the questions you're asking are, so then they will start to look at hallucinations, but it is kind of a prioritization question.
Any more questions?
Is there some sort of generic way to take, say I give you K language models, or like some number of them are not very, or like don't hallucinate very often, but maybe the other ones are like better at task fit. Can you like mix them together and get the best of both worlds?
Good idea. Yeah, I like it. Yeah. And then, yeah, I like it. And the penalized accuracy would be one way to evaluate any of those, to show that it's improving in terms of accuracy and hallucinations. Any other questions? All right, well, thank you again for coming.